Students, this is lesson U5A04a. By the end of the lesson, you should be able to say I can find the lengths of segments using proportional relationships in triangles resulting from parallel lines. And this is the direct application of what's called the Sidesplitter Theorem. So let's take a look. So this right here is a Sidesplitter Theorem, and it can actually be shown that rather than comparing BC to the overall length of AC, the proportional part BC divided by the smaller segment here that's been broken up, right, that AB, is in fact going to be proportional to CD, proportional to CD divided by ED. This is different from corresponding parts of similar triangles are proportional. However, what we're doing here is we're saying that the parts that are partitioned, as it turns out, are actually going to be proportional as well. This is the Sidesplitter Theorem. Let's take a look at a corollary of this. So in other words, another idea that stems from this, okay, that is also useful. As it turns out, if you have any number of parallel lines cut by two different transversals, okay, then it can be shown that the transversals, the parts of the transversals that's broken up, can be shown that they are proportional to one another. So I can say AB is to CD, A over B is to C over D. Similarly, this is also true. Similarly, this is also true. I can say that A to C is to B over D. Can you guys see that algebraically this is also equivalent, right? If I were to cross multiply, right, I'll end up with A over C is equal to B over D. Well, again, another way of thinking about that is geometrically, right? You can compare not only AB to CD, but you can also compare things across, right? A to C is to B to D. See how versatile the Sidesplitter Theorem can be, okay? All right, and yet the last corollary is this, okay? If I have a triangle, like I do here, okay, where the two sides, where the two legs are split in half, okay, then it can be shown that the larger segment is going to be twice as long as that mid segment there. This is actually reminiscent of the Midsegment theorem for trapezoids. If you recall, when we were studying quadrilaterals, there was a mid-segment theorem. This is actually very similar to that, and actually it is the same exact idea, okay? All right, so let's take a look at some examples, okay, that we can apply. So right now, okay, I encourage you to pause the video. The goal is to solve for all the various side lengths here that we don't know. So welcome back. Hopefully you had some chance to think about this. Again, there's many different ways of approaching this. You can say, you can compare x to x plus 3, or you can compare 2 as to 2 to 4. Alternatively, another way of thinking about this, okay, applying the Sidesplitter Theorem, you can also do x divided by 2 is to x plus 3 divided by 4. Either way, okay, you will arrive at the same conclusion. So what I'm going to do is I'm going to do this a little differently, okay, from what I had established, but you're going to see that it actually comes out to be the same thing. I want to set this up using x to x plus 3 is to 2 to 4. Our goal is to find out what all the various side lengths are, okay? So I have x, I'm going to cross multiply to get 4x times 2, or equal to 2 times x plus 3. If I were to distribute, I'll end up with 2x plus 6 is equal to 4x. Subtract 2x from both sides, I get 2x is equal to 6. Divide by 2, I get x is equal to 3. So if x is equal to 3, then I know that this is going to equal to 3, and this is equal to 6. Can you see how everything is proportioned, right? The way that I approached it originally, I had set this up a little differently, I created the proportion horizontally, okay, we end up in the same exact place, however. X still does equal to 3. All right, so let's approach another problem. Okay, here we have a set of parallel lines cut by two different transversals. Again, we can compare these segments in this manner, or we can compare segments in this manner. It really doesn't matter. Okay, so the way that I had approached it in the setup, I did ED divided by BC. Actually, I forgot to say this. Pause the video to see if you can try this on your own. So the way that I approached it is ED over BC. Okay? ED over BC. So I compared it horizontally. Okay, again. You don't have to approach it this way, and as a matter of fact, I think I'm going to approach it a little differently. I think I'll compare it like this. Okay? So I'll do 8 over 3x minus 5 will equal to 10 over x plus 2. And if I cross multiply, I'll end up with 8 times x plus 2 is equal to 10 times 3x minus 5. Distribute, I end up with 8x plus 16 is equal to 30x minus 50. Bring all the x's to one side and everything else to the other. Okay, so I'll end up with 66, because if I add 50 to both sides, I'll end up with 66. And if I subtract 8 from both sides, I'll end up with 22. Divide both sides by 22, I'll end up with x is equal to 3. And if x is equal to 3, so therefore this side over here is going to be 5, and this side over here is going to be 10. Okay? I'm sorry, not 10. What am I saying? It is going to be 4. 3 times 3 minus 5. Can't do mental math. And of course, we end up in the same place if we were to approach it a little differently. Okay, so let's take a look at the next problem here. So in this case, you're told now that we have all of these lines are parallel, because I noticed that all these angles here are corresponding, okay, and they are congruent to one another. And the goal here is to find out several things. Find the side lengths of MN and LK. How many times bigger is IM to JL, HN to JL? What is the length of HN and IM? Pause the video to see if you can figure this out. So hopefully you had some time to think about this. We need to find the side lengths of MN and LK. Let's start there. MN and LK. Okay, which are these segments right here and right here. So again, trusting our understanding of the mathematics here, okay, we can actually compare this to this as to these two together, right? But that would be too many unknowns. Our goal is to figure out what those things are in question, right? So how are we going to do that? Well, I do know this. I do know this length right here is 3. So if that's the case, okay, then I can do another comparison, right? So if this side length is 2, right, the comparison of these two side lengths is 2, then that means the comparison of these two side lengths will be exactly proportional. So ij to jk is 2 to 2. If that's the case, then that means it's 1 to 1, right? So if LM is 3, if this guy is 3, then this guy here should also be 3. And then recognizing, wait a minute, our other task was to figure out what is MN, right? So if this has a ratio of 2 to 1, or in other words, ij is twice as large as hi, And that means LM is going to be twice as large as MN. So this guy right here must be 3 over 2, or 1.5. Okay? So I'm going to write 1.5 over here. Okay, so we're almost there. We finished question A. How many times bigger is IM to JL? How many times bigger is IM to JL? IM to JL. Well, all of these are supposed to share the same corresponding parts, right? So if I compare 2 to 2.5, right? So again, I'm comparing these lengths right here. What must also be true is I can compare 4 to this length, right? So I can say 2 to 2.5 is to 4 to IM. And I can figure out what that length is. So IM, as it turns out, is going to equal to 4 times 2.5 divided by 2. Or IM is simply going to equal to 5. Okay? But of course, we also know this because of the Midsegment theorem, okay, of triangles, because if you notice, you see here, this is 2 and 2, and this is 3 and 3. Then therefore, this segment here must be double that of the one in the middle. Notice that I did not reference the Midsegment theorem of the triangle, and the reason is you don't have to memorize all these different theorems, okay? As long as you have some basic understanding of proportions, you don't have to use every single one of those theorems. You're relying on what you know, right? Some theorems are more useful than others, I have to admit. Okay, and we're going to need to compare again to JL here, right? So JL, okay, how do I find out what JL is? JL, how many times bigger is IM to JL? Well, it's going to be twice as big. We already established that. And then HN to JL. HN to JL. Okay. So HN, okay, compared to the overall length right here is going to be 5. Is going to equal to, again, because they're all proportional, I'm going to compare this, is to 2.5 over 2. So how many times is HN going to be bigger than JL? It's going to be 5 times bigger, right? Because 5 times 2.5 divided by 2. Actually, no, I take that back. It's not going to be 5 times bigger. It's going to be whatever that is. So this is going to turn out to be 12.5 divided by 2, or it's going to be 6.25. So if this is 6.25, right, and I know that that segment there is 2.5, it's whatever that figure comes out to. All right, so now that I know this, okay, we need to know what is the length of HN and IM. HN and IM. We figured all this stuff out already. So that's pretty much it. The way that I had approached it originally, so I set that LM to LK is going to be proportional to one another. So y is equal to 3. It's going to be twice as big. 6.25. Yeah. Okay? All right.